Welcome everyone to PALS. Today's speaker is Paolo Agliano, who will speak to us about splittings and yet another generalization of Baker's finite basis theorem. Paolo, please.
Okay, hi guys, and thanks for having me. And this is a part of an ongoing research with Alex Chitkin, and we are sort of gunning for the paper written by two people with the highest sum of ages, because we 141 in two, so not bad. And this is a sort of a spin-off of the research we are doing. I mean, we were studying different but related things, and we came up with this result. It's a nice little result, and it's suitable for a seminar like this. So what is the idea? What is the idea? We will talk about splitting in lattices of quasi-varieties, and then we'll try to say what we can do with it. And of course, the concept of splitting is a very old concept. I mean, dates back to the 40s. And it's sort of, you know, what is a splitting pair in a lattice? Where a splitting pair is a pair of elements such that L is the disjoint union of the ideal generated by A and the filter generated by B. And in this case, I mean, A has to be strictly mid prime and B strictly joint prime, or completely mid prime and completely joint prime. I don't know how you want to say it, but it's the same. The idea that this concept lay dormant for about 20 years, and then Ralph McKenzie revamped it, and you know, he used it to study varieties of lattices, basically. Okay, and then from then on, this concept has been applied a lot of times to lattice of subvarieties, but not very often to the lattice of sub-quasi-varieties of a quasi-variety. Well, because I mean, sub-quasi-varieties are harder, right? The lattice of sub-quasi-variety of a quasi-variety can be horribly complicated, as JB knows very well, because he's written a book about it. So, I mean, now, the three main definitions we've used are the concept of relative congruence, which we call Q congruence. The Q congruence is just a congruence of an algebra such that the quotient belongs to the quasi-variety. And I mean, it's an old result by Maltsev, I think, that the Q congruence is for an algebraic lattice, which we will denote by con Q of A. And an algebra is Q reducible, relatively statically reducible, if this con QA is a unique minimal element greater than the bottom. So, I mean, it's just the relativization of subdirectly reducibility. And an algebra is weakly Q projective in Q. Well, if for all B in Q, if A is homomorphic image of B, then A is a subalgebra of B, which is slightly weaker than ordinary projectivity, right? So these are the three main definitions we are going to use. Now, the theory of splittings in lattices of quasi-varieties is totally similar to the one in lattice of subvarieties, because I mean, basically we can sort of go through the standard argument, right? If we have a splitting in the lattice of sub-quasi-varieties, and we take the quasi-equational theory of the left member of the pair, then okay, this is the intersection of all the models of each quasi-equation that is in sigma 1, right? And I mean, Q is completely mid prime because it is a splitting. And so, I mean, really, Q is axiomatized by a single quasi-equation. On the other hand, I mean, you know, every algebra is embeddable in a microproduct of its finitely generated subalgebras, each of which is a subgroup product of necessarily finitely generated Q reducible algebras. So, what do we have? Well, we have that Q2 is the join of all these things, right? But again, Q2 is completely joint prime. So it's really equal to the quasi-variety generated by one of them. So far, I mean, there is nothing really new. What is a Q-splitting algebra? Is a finitely generated Q-reducible algebra such that there is a quasi-variety which is the left part of a splitting pair, okay, where the right part is the quasi-variety generated by A. And in this case, you know, we talk about splitting quasi-equation, and we can call Q of A the conjugate quasi-variety if you want. Here it is. But, you know, what is clear is that if I have a splitting, is always something like this. Okay, so if I have a splitting in the lattice of some quasi-variety of a quasi-variety, then there always exists a finitely generated Q-reducible algebra such that the splitting pair is exactly of this kind. Okay, so all these splittings are described by this group. Now, you know, for quasi-varieties, for varieties, we have, you know, that if a variety is generated by its finite algebra, then every splitting algebra is finite, right? And I mean, we have exactly the same for quasi-varieties, only we have to have a different, we have to use a different property, which is the finite extension property. And a quasi-variety has a finite extension property if for every algebra there, and for every finite partial subalgebra, then there is a finite algebra in which F embeds. So this is, again, is a very well-known concept, but the lemma is quite obvious. If Q has a finite extension property, then every Q splitting algebra is finite. So far, nothing really new. Now, we have to be a little bit careful about finite presentations. Now, what is a Q finitely presented algebra? Okay, now here I have a very technical definition, but the point is that I don't want to read this stuff. I mean, it's really there just to see that, you know, you see that I've done my homework, but I don't really want to read it. But the bottom line is that, I mean, through a technical definition, I can prove that a Q finitely presented algebra is exactly what it should be. In other words, if Q is a quasi-variety, for any finite sets of variables and quasi-equations, then there is exactly one algebra that is Q finitely presented by this pair. We can denote this algebra by FQ of X sigma, and we may assume that the embedding that we were defining here, okay, this function can be taken to be the identity. And if this is the Q congruence generated by sigma in FQ of X, in the free algebra over X variables in Q, then this is exactly what it should be. I mean, the quotient of the free algebra through that congruence. And finally, an algebra is Q finitely presented if and only if is a quotient of a finitely generated free algebra by a finitely generated Q congruence. So this is just to justify that we call these things Q finitely presented because they are. I mean, they are what, you know, they should be. Okay. Now, let's define this. Okay. We define this class. This is the class of over algebra in the quasi-variety in which A does not embed. Okay. Now, we have a standard lemma. Okay. So if A is Q reducible and Q finitely presented, then this class is a quasi-variety. If A is also weakly projective, then this class is a variety. Moreover, if Q is locally finite, then both Conver implication holds. So we can prove that if Q is locally finite and Q of A is a quasi-variety, then A is Q reducible. And if it is a variety, then A is weakly projective in Q, of course. Okay, so the proof, I mean, I'll show you maybe a part of the proof. For instance, let's suppose that A is Q reducible and Q finitely presented. By what we said before, it is a quotient of a finitely generated free algebra modulo a finitely generated Q congruence. Okay, so let's take the characteristic quasi-identity of A, and then, you know, we had this lemma, right? Here. Okay, so if an algebra is Q reducible and Q finitely presented, then for every algebra B in Q and for every phi, which is a characteristic quasi-identity, then B is not a model of phi if and only if A is a subalgebra of B. So using this, it's almost straightforward, right? We get at once that this is just a class of models of phi. And since phi is a quasi-equation, this is a quasi-variety. If A is also weakly projective, then if B is an homomorphic image of C for some C in Q of A, and A is a subalgebra of B, then A is a subalgebra of a homomorphic image of C, which of course is a homomorphic image of a subalgebra of C, right? And so A would be a subalgebra of C, which is impossible. So, because you see, I'm assuming that A is weakly projective. So if A is H of something, then it is a subalgebra of that something. So the conclusion would be A is a subalgebra of C, which is impossible, right? Because you're assuming that C is in Q of A, and Q of A consists of all algebras in which A cannot embed. So that's basically the proof. And the other parts are totally similar. We simply use the normal properties of being Q finitely presented and Q reducible. Nothing major. So what are the what is the corollary? In any quasi-variety, every Q finitely presented Q irreducible algebra is splitting with conjugate quasi-variety Q over A. So every Q finitely presented Q irreducible algebra, which means that there are a lot of splittings, right? Because I mean, if you take a variety of a quasi-variety of finite type, and you take a finite algebra, then it is finitely presented. So you take all the finite relative selective reducible in the quasi-variety, as long as the quasi-variety has only finitely many operations, those are all splitting algebra. So there is a lot of them. Okay. And the proof is, okay, we prove that if Q is finitely presented and Q reducible, then this class Q over A is a quasi-variety. Of course, A does not belong to that class. And let's suppose that A is in Q prime and Q prime is not contained in the Q of A. Well, then there is a B in Q prime such that A is a subalgebra of B. But then A would belong to Q over A, which is again a contradiction. So Q prime is contained in Q over A, and A is splitting with Q of A's conjugate variety. This is really a very standard argument. I mean, very easy to see it. All these proofs are elementary. Now, the requirement of BQ finitely presented is necessary. So finitely generated is not enough, right? Because if we let's take any quasi-variety with the finite extension property, then of course, I mean, Q is generated as a quasi-variety by its finite algebras, just because of the definition of finite extension property. It's almost automatic. So if I take an infinite algebra there, then it cannot be a quasi-variety, and Q over A cannot be a quasi-variety because all the finite algebras are there, and they generate the entire variety, so the entire quasi-variety. So it's clear that that cannot be a quasi-variety. So, I mean, finitely presented is necessary. However, if you want really to be to look at finitely generated, then we have to add an hypothesis, and not surprisingly, the hypothesis is that the algebra be weakly projective. So if I take a finitely generated algebra which is weakly projective and Q reducible, then A is Q splitting, but in this case, the conjugate quasi-variety is a variety because of the lemma I proved before, right? No, sorry. This one. Okay, so if it is Q reducible, Q finitely presented, and weakly projective, then that class is a variety, right? So if I take a finitely generated weakly projective algebra, it has a conjugate variety, not a subvariety. I mean, it's a variety. So now that we have talked about a little bit about the general properties, now let's try to do something with it, right? What can we do? Well, okay, take a quasi-variety, right? And consider the class of all splitting algebras in Q. Now, we can define a quasi-ordering in the obvious way. A is less than B if and only if A belongs to the quasi-variety generated by B. That's a quasi-ordering, so it's got an associated equivalence relation and an associated partial ordering on the equivalence classes. And as usual, we denote the partial ordering using this funny symbol, which is, I believe, pre-check in LaTeX. And well, if a prime is splitting for Q, we can find always a Q irreducible algebra which generates the same quasi-variety, because all the splittings are of this kind, right? So really, we may assume that all the splitting algebras are Q reducible, and that QSFEL, the class of splitting algebras, is partially ordered by this ordering. Okay. Now, first thing, okay. Let's take an anti-chain in this ordering, and if I take two different subsets, they generate different sub-quasi-varieties. Okay, this is the first lemma. I'm not going to show you the proofs because I mean they are mostly elementary, except for one or two. But the consequence is interesting, because if I have a quasi-variety such that the class of splitting algebras contains an infinite anti-chain in that ordering, then this lattice is not countable. Okay, so it's uncountable. Now, that's the other thing. However, if I take a class of finite algebras, so if they are all finite, then A contains a minimal anti-chain. So this is what makes things work in a way. I mean, it's not really surprising, but it's useful. It's useful. Okay. So let me tell you this again. Okay, take a class of finite algebras that are splitting. Then this class contains a minimal anti-chain, minimal in the obvious sense, anti-chain with respect to the ordering. Now, let's take a quasi-variety. Okay, we say that a sub-quasi-variety has an equational basis relative to Q if there is a set of equations such that this is true. Okay, so we want to look at quasi-varieties that are relative subvarieties, right? That's what they are. Okay, and we say that the quasi-variety is primitive if and only if for each quasi-variety contained in Q, then Q prime is the intersection of Q with the variety generated by Q prime. Now, it's almost immediate that a quasi-variety is primitive if and only if every sub-quasi-variety of Q has an equational basis relative to Q, or if you prefer, if and only if every sub-quasi-variety is a relative subvariety. I don't like to use the word relative subvariety because, I mean, if you say subvariety, implies that it is a variety, and this is not a variety. So I don't like to use the word relative subvariety, okay? But, we have this famous result by Gorbunov. I mean, actually, it's much longer than this. I just extracted what I needed. Okay, if I take a primitive quasi-variety, then any Q finitely presented and Q irreducible algebra in Q is weakly projected. Okay. Moreover, it's not written there, but I tell you anyway, if it's locally finite, the converse holds. Okay. So if I assume that Q is locally finite, then it is an if and only if. Now, the point is that if I have, if it is a relative quasi-variety, or the conjugate quasi-variety can be defined relative to Q by a set of equations, really. I don't need quasi-equations because I know that, the entire quasi-variety is defined by equation relative to Q. So I don't need I don't have a splitting quasi-equation. I do have a splitting equation. Okay, that's the point. In other words, every splitting quasi-equation is provably equivalent to a splitting equation. So I may just assume that there is a splitting equation. Now, by what we proved, in this case, the conjugate quasi-variety is really a variety, again, okay? Now, this is the main thing that we can prove using this setting, okay? So we take an interval in the lattice of sub-quasi-varieties, and we can prove this. Okay, let Q be a primitive quasi-variety of finite type, and let Q prime contained in Q such that every quasi-variety in the interval Q prime Q has the finite extension property. Then the following are equivalent. Okay, every sub-quasi-variety in the interval has a finite equational basis relative to Q. The interval is countable. The split, I mean, the set of splitting algebra in Q that are not splitting in Q prime has no infinite anti-chain, and the interval enjoys the descending chain condition. I mean, really, the interesting part is 1 and 2 are equivalent. Because you see, I mean, it's very easy. I mean, it is a standard exercise, right? For instance, take any quasi-variety that has a finite lattice of sub-quasi-varieties. Then it is a standard exercise to prove that every sub-quasi-variety has a finite relative basis of quasi-equations, of course, in the general case, right? So this is, I don't know, I believe it's even in some textbook, but it's well known, okay? Now, in this case, we have a little bit more because, I mean, we have the situation in which we can consider not only the finite case, but also the countable case. So what is the real deal here? Well, okay, if Q is locally finite, then all its sub-quasi-varieties have the finite extension property, right? Because, I mean, if a quasi-variety is locally finite, has the finite extension property, that's by definition. And if a quasi-variety is locally finite, any of its sub-quasi-varieties is still locally finite, so it has the fact. So, these conditions are satisfied. This condition is satisfied for the entire lattice of sub-quasi-varieties. And, well, we have this. For a primitive locally finite quasi-variety of finite type, the following are equivalent. Every sub-quasi-variety of Q has a finite equational basis relative to Q. The lattice of sub-quasi-varieties of Q is countable. The splitting algebra have no infinite anti-chain in that ordering we have defined, the natural ordering we have defined. And this lattice enjoys the descending chain condition. We can derive another corollary, which is, I think, less interesting, and I'll explain you why. Okay, let's take a primitive quasi-variety of finite type. Is Q has finitely many Q irreducible algebra, then every sub-quasi-variety of Q has a finite equational basis relative to Q. Now, why this is not so super? Well, because in a way, I mean, it was already known, in the sense that, okay, the idea, the reason why the corollary work is because with this hypothesis, the lattice of sub-quasi-varieties of Q is finite. So in particular is countable. Okay. So the hypothesis, the corollary can be applied. But the idea here is, okay, I told you before, and I tell again, I mean, if the lattice of sub-quasi-varieties is finite, then every sub-quasi-variety has a finite basis relative to the quasi-variety, and by basis in this case, I mean quasi-equational basis. But of course, if it is primitive, this quasi-equational basis can be transformed easily into an equational basis, right? So this is not so fantastic. I do like the first corollary more. The idea is that, okay, primitive is necessary, right? Because, I mean, first, this can be seen as some version of Baker's finite basis theorem, the one about, relative congruous distributive relative congruous distributive sub-quasi-varieties in Pigozzi. And then I believe that also Selakowski and Zobiak proved something close to it. But here, I mean, we don't need Q-congruous distributivity, but we had primitivity. So somehow, I mean, since there are primitive varieties that are neither Q-congruent distributive and not even Q-congruent modular, there are examples, maybe, okay? Now, primitivity is essential, of course, right? Because, for instance, Rybakov produced a finite eigenalgebra that doesn't have a finite quasi-equational basis relative to the variety of eigenalgebras. Now, of course, the variety generated by A is congruence distributive, so U of A is a finite equational basis relative to the variety of eigenalgebras, and of course, Q of A cannot have a finite quasi-equational basis relative to the variety generated by A, otherwise, putting together the two bases, if to have a finite basis relative to the entire variety of eigenalgebras, which doesn't. Okay, so this is an example. Let me stress that this is not the only example. There are even older examples than this. I think that Belkin in the 70s and Tumanov proved that the same result for lattices. So there is a finite lattice that does not have a finite quasi-equational basis relative to the variety of lattices. And then I think Zobiak found an interior algebra with the same property. And finally, I think Selakowski and Zobiak found a subdirectly reducible lattice with this property. Because the lattices by Tumanov and Belkin were not subdirectly reducible. So, so really you need primitivity. Okay. Final thoughts about it. Okay, how can we use this, right? Because this clearly applies to locally finite quasi-varieties in which the lattice of sub-quasi-varieties is counted. Of course, if the variety is relative congruence distributive, there is nothing new. I don't know about relative congruence modular, but I do believe that Keith and Ralph McKenzie did some stuff about this in the late 80s, early 90s, because I remember we were together in Hawaii, and I remember you, Keith, working on this, on the relative commutator or something like this. So I haven't looked into it. Of course, if you look at varieties, this simply says that a primitive locally finite variety in which the lattice of subvarieties in this case, because if we consider a variety, primitive means there are no subquasi-varieties. Every subquasi-variety is a variety. So if I have a primitive locally finite variety in which the lattice of subvarieties is countable, then I have this property. And of course, if the variety itself is finitely based, then every subvariety is finitely based. But again, this is useful only if we apply it to something that is neither congruence distributive or congruence modular for varieties. For quasi-varieties, I don't know, but there are this might be interesting to see how these things interact with the results that we have about primitive varieties of modules. For instance, there is this thing that you take a module over a Dedekind domain. Okay, you take the variety of modules over a Dedekind domain, and the quasi-variety generated by the Dedekind domain as a module over itself is primitive. Okay, and what below, it doesn't have any proper sub-quasi-variety, only varieties. So all the sub-quasi-varieties of Q is not a variety, but all its sub-quasi-varieties are varieties, and they are in one-to-one correspondence with the ideals of the domain. Okay, this is a combination of a series of results by, I think, Belkin and Jedlica and other people, but it boils down to this. So it might be interesting to look into it. This is clearly a work in progress, and you might say that, it's not much, but it was a nice thing. I didn't expect that at all, because I did not really expect to find results about finite basis using primitivity. Maybe I should have, but it really didn't come to my mind, and so I was rather surprised when we found this. So, well, I think that I can say just thank you and wait for your questions.